time is the quantity which physicists can measure more accurately than anything else, but it's the biggest mystery. They can't agree on what it is. It's really quite surprising. So let me just give you an overview, and my talk is, as you see, does time exist, or in what sense does it exist? And it's going to be a personal point of view, at least towards the end. So let me give you an overview. I want to give it in a broad historical sweep. As you see, I'm going to start with the pre-Socratics and go through to Newton at a pretty good rate. Newton certainly deserves a bit of attention, and so does the critique before Einstein of Newton's concepts, because that's very much related to what I want to say. Then we'll talk a little bit about Einstein's relativity revolution, and then the quantum revolution. And what really makes time mysterious is trying to reconcile those two together. And I shall finish by talking about two routes to time without time, how we have this very vivid appearance, strong feeling that there is time and it's passing, but somehow or other we just can't put our fingers on it. So where does that come from? There were two very contrasting views already over 2,500 years ago. Heraclitus is famous for saying, all things move and nothing remains still, and you cannot step into the same river twice. That's a very striking saying. And then Parmenides, much the same sort of time, he insisted that existence is timeless and change is impossible. Now that seems to be a manifest nonsense, because I think you see me walking around on the stage. So how are we going to make any sense of that? So the person who is really very important in this, I would say, is Plato. Many people regard him as the greatest philosopher of all time. He was strongly influenced by Parmenides, and he distrusted the fleeting sense perceptions, and he believed in perfect mathematical forms. And let me just show them you here. These are the famous 5 Platonic solids. By pure thought, that you can work out that there are these perfect solids defined mathematically. There are just 5, there can't be more. And this leads to the idea that there are mathematical objects in a Platonic heaven, a Platonic realm, which somehow or other exist independently of humans. It takes us humans to find them, but when humans do find them, they are convinced that somehow or other they've discovered something which was there before. They didn't invent it, they discovered it. Through thought. And that had a huge influence on Plato and still to this day. So let me just in this say why I think you can see already why being is perhaps more fundamental than becoming. Just think about a movie. You could cut the film up into stills and throw them down in a heap, and actually nothing objective in the story is lost. You could put it all together again just by the continuity in the thing. And so you get the impression that somehow or other the real thing is the structure in the stills, and somehow the idea that something is moving is much more fleeting and harder to get hold of. And of course you could say, well, I've left out the projector and you sitting there watching the film. But you could take pictures of the projector and the brains in your head, and you'd be back in the same situation. You'll never get down to actually understanding the change in the things. You have to see something changing before you realize that something has changed. And it's the difference between my hands here and my hands here that you see. So that's one of the dilemmas and why time is so elusive. It's just sitting in that fact there. So let me turn over the page and see what I've got coming next. Ah, yes, it's good St. Augustine. What then is time? If nobody asks of me, I know. If I wish to explain to him who asks, I know not. That is so true. Lots of people think they really know what time is, but press them and they're very hard, find it very difficult to explain. Now, what he did say, and that I think is really a wonderful thing, he as far as I know, he was the first person who said it, but it's a very profound answer to an interesting question, because by that time the Christian religion had got well established with the idea from Genesis that God had created the world out of nothing. And people were asking, well, why did God create the world just precisely when he did and not 10 minutes earlier? And Augustine came up with an absolutely brilliant answer. He said, God did not create the world in time, but with time. If there is no world, there is no change. If there is no change, you can't begin to talk about time or be aware that time is passing. So I think this was a very, very profound insight. And it is actually very much at the heart of Einstein's general theory of relativity. In some ways, that captures that response of St. Augustine. Of course, he didn't have the mathematics that Einstein put into it. But without the hurly-burly of the world, there certainly is no time. There's no change and there's no time. So now we jump forward over 1,000 years to Sir Isaac Newton. I love this portrait. I just think of it as an eagle surveying the whole landscape of the earth and comprehending everything in one glance. Absolute true and mathematical time of itself and from its own nature flows equably without relation to anything external. And this actually corresponds very closely to the way that a lot of people think about time. But I would say it's complete and utter nonsense. And I speak as an Englishman. Absolute space, he said, in its own nature, without relation to anything external, remains always similar and immovable. Now, why did Newton make these statements? And let's get clear, which he says later on in his famous Principia. He grants that absolute space and time are invisible. But why he wants to have this fixed space, now the fixed space is the really important thing. The time is also very important, but he wants something like the solid walls of this room, which are not moving relative to each other, because in that framework, he wants to formulate his first law of motion, which he could already see. If he could formulate this first law of motion, it would be the foundation of dynamics. And that is what it became. And he wants to be able to say that every body continues in its state of rest, or uniform motion in a straight line, unless something biffs it off that motion. Now, you can't talk about a straight line unless you've got a rigid framework in which to say that. And that's fine in this room. I did more or less succeed in moving my finger in a straight line across the room. So he needs that framework. And he needs a clock or something to say that it's moving uniformly. Without those two things, there's no content to that. But the real problem, which Newton clearly realized, but he never properly explained how he could get around it, was the fact that these two things are just plain invisible. You can't see them. You can see me, you can see each other, you can see the walls of the room, but you can't see space. And that led to immediate criticism from Newton's famous contemporary and rival. They got into terrible arguments about who had first created the calculus. Leibniz. And Leibniz came up with a totally different view of what space and time are. And although he lost in the short run his argument with Newton, I'm convinced that Leibniz is much, much closer to the truth than Newton was. Leibniz says space is the order of coexisting things, and time is the succession of coexisting things. Now let's see if I can get across what he meant by that. Let's just have a toy model of, well, let's first of all think of three particles moving in this room, and in any instant they will be at the vertices of a triangle. Now in this room, this hall, each particle's position is defined by 3 coordinates. So there's 9 coordinates determining the position of the 3 particles in total. and then I'm holding this up at a certain instant of time. According to my chronometer, it's 27 minutes past 7. So that's okay in this room if you can see the walls, you know what you're talking about. But Leibniz asks us to envisage the situation where my 3 particles are everything. And then there's no walls of the room to say where they are, what they're relative to. All you're left with is the distances between the particles. And that is what Leibniz meant when he said that space is the order of coexisting things. You have 3 particles which are there at once, and they have certain distances between them, and that's all there is. And you can't imagine moving, he says you can't imagine moving this thing 6 foot to the left. That's nonsense, because nothing objective changes. So that was Leibniz's objection to absolute space. And then for time, he said, well, if I've got 3 particles, well, the distances between them will change. Now, these 2 triangles are not the same, so they're different. So when Leibniz says time is the succession of coexisting things, this is one set of coexisting things, and this is another. They are different, and the passage of time is just the change from that one triangle to another. That configuration has changed. So I think this is really much closer to reality, and we shouldn't get bamboozled by scientists and the likes of Newton into thinking that we can abstract away from the real things in the world. That's the last thing I would like to do. What, though, happened was that Newton's laws triumphed, and the reason they triumphed was they were not verified relative to absolute space or time. They were verified relative to the distant stars. You could verify that objects left to themselves would travel in straight lines relative to the framework defined by the distant stars, and they would move uniformly relative to the clock provided by the rotating Earth, the rotation of the stars in the sky, as we now understand that as being due to the rotation of the Earth. And that was actually what was empirically verified. It wasn't Newton's laws relative to invisible absolute space and time. But people settled down and they accepted Newton's view, and they came to believe firmly that absolute space and time did exist. And then along came somebody called Ernst Mach, about 130 years ago, published a very influential book in 1883 where he criticized Newton's concepts, and that was the great stimulus to Einstein's creation of the general theory of relativity. And I want to tell you, read out 1 or 2 of the things he said. Of time, he said, it is utterly beyond our power to measure the changes of things by time. Quite the contrary, time is an abstraction at which we arrive by means of the changes of things. And that I feel pretty confident. I'm close to saying I would take poison on it. That's right. And also he says, we have knowledge only of relative spaces and motions. The universe is not twice given with an Earth at rest and an Earth in motion, but only once with its relative motions alone determinable. Now, he came up with a really radical idea. He pointed out the fact that I've already said, that Newton's laws were actually verified relative to the distant stars in the universe and the rotation of the Earth. And he said this inertial motion that Newton had identified and played such a key role in Newton's theory was the particles executing that inertial motion. They were not being guided by absolute space and following straight lines in absolute space, but in some way that he could not identify exactly how it was, they were being guided by the totality of all the masses in the universe. And this was a fantastic revolutionary idea which greatly stimulated Einstein, and he gave the name Mach's principle to it. So this was really completely changing the way people were going to think about the universe. It opened up a totally new perspective on the way of thinking about the universe, and in a way knitted it together into a holistic totality. And somehow or other you have to assume that the universe in some senses is a closed system. Shall we say, now that we can imagine that space is curved, three-dimensional space can be curved so that you can go off in that direction in principle and far enough and you'll come around and hit yourself in the back. I mean, if somebody else goes off, my twin. But it's like the surface of the Earth. You can walk in principle all the way around the Earth and come back to where you started. So to implement Mach's ideas, you want this idea that the universe is some closed system, and somehow or other it's all in a very intimate interaction with itself. Everything is interacting with each other in a very tightly bound way. And also that time comes out of how the things change. And let me just illustrate. I'm going to show one equation or two equations later on. But let me just say how time comes out of this and how actually time does come out of it, both in Newton's theory and in Einstein's theory, without any reference whatsoever to some invisible river of time flowing like that. Let me just go back to these two triangles. What time is really like, what duration is, a length of time, in this picture is that if I've got these two triangles, they're different, and I try and bring them into closest agreement. I call this process best matching, where I'm trying to bring them as close as I can to overlap. But because they're not congruent, they're not identical, I can't bring them exactly to overlap. But there's a little bit of difference left over. And that is the basis of how dynamics works in Einstein's theory. It's also really in Newton's theory. And it is also an explanation of what time is. Time is just some particular way of quantifying that difference, that inability of mine to bring those two triangles to exact coincidence. So time is a measure of difference between two configurations. And I have a very concrete notion of what an instant of time is. In this toy model of mine of just three particles, it is literally a triangle. It's the configuration of the three particles. So there you like, there's one instant of time, and there's another one. So in one sense, I'm a time denier, but I'd like to claim that I'm an enricher, a great enricher of time, because I'm saying this is what time is, it's something real. You're part of time, and I'm part of time. And we're generating duration by moving around. Every little movement in your body is contributing to time, to duration. It's helping to make 1 second. And the laws that govern the way we all change and move is actually, ultimately, when you analyze it, you can see why it is that you can say meaningfully that a second today is the same as a second tomorrow. It comes out of the marvelous way the universe works, and it's how it's governed in its evolution. So let me go on to the next figure I want to mention. This is the great French mathematician Henri Poincaré. And in 1898, he identified two problems relating to time. One was the problem, how do you define duration? This is what I've just said. What does it mean to say that a second today is the same as a second tomorrow? And the solution he came up with was essentially what I've just illustrated to you in very qualitative terms with those two triangles. It's a difference between configurations. And he gave a formula for that. And I would say there's no question, at least before we get into quantum mechanics, at least at the level where we're still before the quantum revolution, and basically for everyday purposes we do live in the non-quantum world, I would say that that's correct. And that was the quantitative expression of this idea that goes back to Mach. But then he said there's actually another problem which hardly anybody has noticed, is how can I justify saying that now here is the same as now in the Andromeda Nebula? This is the problem of how do you define simultaneity at spatially separated points? And that was a really new insight. One or two people had sort of half realized that before Poincaré. Now that's the problem which Einstein solved brilliantly in his 1905 paper in which he created the special theory of relativity. Actually, Poincaré solved it simultaneously, but gets much less credit for it, partly very unfairly. There are historical reasons for that, partly because Poincaré actually was a rather conservative mathematician and physicist, and he didn't accept the implications of it in the way that Einstein did. Einstein did it with fantastic aplomb, and in a way deserves to be so associated with it. So the interesting thing, I think, is that Einstein never really seriously thought about the problem of duration. And he was very keen to go on from his first success with the special theory of relativity and create a theory, first both of gravitation and also that would implement Mach's idea about where inertia comes from. But he set about it in an indirect way, and that's historical. There are lots of reasons, and I haven't got time to go into that. So I'm just going to mention that there's a picture of Einstein. As I say, he solved the simultaneity problem brilliantly, but he made no direct attack on the problem of what is duration. And he combined a very important aspect of his thinking when he was thinking about the problem of simultaneity was to take into account the relativity principle, which had been discovered hundreds of years earlier, formulated by Galileo, where there's a wonderful gem. Galileo was a fantastic writer, one of the greatest Italian writers. And in one of his dialogues, there's a marvelous passage where he invites you to imagine going down into the cabin of a ship which is sailing at uniform speed, and you do various experiments with, what has he got here, all these flies, butterflies, and other small animals. And you do experiments with them when the ship is still in the harbor and when it's sailing uniformly. And you can't see any difference if the curtains of the cabin are drawn. The things unfold in the cabin in exactly the same way. That's the relativity principle. And Einstein, in a very brilliant way, combined that fact with certain properties about the way light behaves and came up with this wonderful theory. And then this led on to one of the most daring innovations in physics, which I dare say many of you know about, by Hermann Minkowski, in a very famous lecture in 1908, where he came up with the idea of space-time. He fused space and time together into a four-dimensional block. He said, really, time is just like space. It's essentially the same thing. And he has this, he wanted to be famous. He was really keen on this. I mean, with good reason. He was a very great mathematician. And he had this great insight. And it's known he spent a lot of time preparing the opening sentences of his papers. It starts with the claim that what he's going to say rests on a very firm foundation of experimental facts. And then comes this fantastic sentence. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. And that is just engraved in the soul of every theoretical physicist. And it's very hard for them to shake it off, but I suspect they may have to. I'm inclined to think that this great idea of Minkowski's was a glorious historical accident. And that's because he made time into something identical to space. And I just don't believe it. Time is something to do with things in space changing. It's not space. I really do believe it's different. And certainly there's a strong case can be made for it. I'll just show you this one diagram here. This is space-time. So the horizontal direction, only one dimension of space is shown. So one has to throw away two of the dimensions of space to show it. And the vertical one is time. And the great thing about the revolution that Einstein and Minkowski introduced is that you can divide up space and time in any way you like by these lines here. You can tilt this line and divide and say, this is the line of simultaneity. These points along here are at the same time, or these ones along here. And that's Einsteinian relativity. And Machian relativity is something quite different. It's saying that in any of these time slices here, what really counts, what defines the position of this object is its distance from every other object in the universe. That's a completely different thing. And when Einstein set out to implement Mach's ideas, he set about it in a very indirect way basing it on this Minkowskian idea of relativity as opposed to the Machian one. This picture is what's called the block universe, and it destroys any idea that there's a unique history in the universe, that one configuration, one state of affairs follows each other's quite definitely. Because if we're saying, if we've got one of these time slices here, so my hand is now, this is a state of affairs now. But if I shift and go to the other thing like this, the hand in this position is no longer simultaneous with my hand where it was like that. So I can no longer say that this thing is followed by something definite. There's no way of saying how things definitely follow one another in the universe. Now this is very counterintuitive for us because we feel that time unflows in a definite linear fashion and we see just one thing following another. And this was destroyed by Minkowski's idea. And so it destroyed the notion of history, and the only way that you could think of was that the whole of space-time exists all at once there like a block. And this is going straight back to Parmenides, who says that change is impossible. And it's just one thing which is given and is timeless. I'm just briefly going to mention the great mathematician Bernhard Riemann, who in 1854 developed the theory of curved space. This was a great revolution. It had been anticipated by work that preceded it, but basically people had thought for 2 millennia and more that space must be Euclidean and must be flat, so to speak, like in 2 dimensions, a flat surface, only in 3 dimensions. But then mathematicians realized that needn't be the case, and Riemann made a change which on the face of it seems very, very small, but actually is unbelievable in the consequences that it has. He says space in small regions, and he's talking about 3-dimensional space like you and I think of space, is flat like Euclidean space, but it can be curved. And this would be just like the smooth surface of the Earth. So just imagine the surface of the Earth is completely smooth. If you look in a small region, you could not tell that it's not flat. But go further afield, and then bit by bit, you see that it is curved. And that seems quite a modest change. But then he envisaged that this curvature could change in all sorts of ways, as it does on the surface of the Earth. You have all this different curvature on the surface of the Earth. And then the idea later came that this curvature could change, that it could fluctuate and in accordance with definite rules. And this is what is actually implemented in Einstein's theory. So now you have a very, very, very much richer situation. You don't just have particles or atoms moving around in a rigid, flat, 3-dimensional Euclidean space. You have space itself changing and twisting and getting more or less curved, and matter fields interacting with it. It's all a hugely rich interacting system. And the way I think one should look at it, all of this rich interacting system of matter and geometry is what creates time in a much, much more sophisticated way than I showed you with those 2 triangles. So this is a huge revolution, and it's really wonderful what comes out of it and what beautiful equations Einstein found to describe it. So let me now say how I think, just a little bit different, how Machian dynamics should be described. This would be, we can think about this without going to curved geometry. Just imagine a whole lot of points like this, point particles, that all that counts is just the differences, the distances between the particles as you see them there, and they're changing. It's like a swarm of bees swarming in nothing. You haven't got the reassuring framework of the walls to tell you where the bees are. All you've got is the differences between, the distances between the bees that are changing. And somehow or other you've got to find a law that describes that. And that's really what the Machian problem is about, and which Einstein didn't attack directly. But what you can do is, I'll just briefly sketch it to say that it can be done, is essentially with 3 particles, you can do what I was saying about best matching. The law is based on the idea that you constantly, if you have two triangles which are nearly the same, you can measure the difference between them by this process of best matching. You try to bring them as close as you can to overlap, and then you get some number which measures the amount by which you fail. Now you can imagine you have two triangles which are very different, and you want to interpolate between them by a smooth succession of triangles which pass smoothly from this one over here to this one over there, and in the process you want it to happen so that this amount of incongruence as you go along is minimized, that it's the smallest amount that you can make, and that is then the history of a Machian universe. And it's completely got rid of Newton's absolute space and time, because all it relies upon is moving the two triangles. Each time you've got two neighboring triangles in your string, you move them into the best matching position. But once you've done it, it doesn't matter where you put it. It's what you can call background independent. So you've just got this possibility of describing change without any framework in which you have to do it, which Newton thought was unavoidable. So it can be done, and that is sitting inside general relativity. So now I'm going to, and then what you can then do is then you can imagine putting one triangle on top of each other in the best matched position, one after another like that, as I've shown in the slide here, and then the vertical separation can be that time difference that you get, again, which is a measure of the difference between the two. And when you've done that, you've stacked them like that, and it turns out that you recover exactly Newton's law of motion of the particles as they go up in this framework, but that framework was not there at the start. It's after the event, after you've gone through this process. So you've created what looks like a framework, but it wasn't there before. It's out of the law of dynamics, which tells you how the triangles change. So that's what you can, how you can do it. So now it's time to get on to quantum mechanics. Now, I'm going to go through the key figures in quantum mechanics very, very briefly. It started with the discovery of Max Planck. A crisis had developed because it seemed that you would need an infinite amount of energy to bake a loaf of bread in an oven. And Max Planck hit upon a very drastic way of resolving this problem. He suggested that energy was not emitted continuously by the atoms in the side of your oven, if you like, but in little chunks. There were quanta of energy, as he called it. And when he did that, he actually calculated how the energy would be distributed in an oven at a given temperature, and he got the right answer. And it wasn't really noticed all that much, but Einstein noticed it 5 years later and developed what later became the notion of a photon in a very brilliant paper, which actually came out before his special relativity paper, and is the one that he decided he called, that was a bit revolutionary, he said, and very right too. Then the next development after Einstein's 1905 paper was Niels Bohr, the great Danish physicist, who came up with a model of atoms, and he explained the spectral lines that the hydrogen atoms emit. So that was the next step. And then there was a lot of very confused period until the two creators of quantum mechanics came along. First of all, Werner Heisenberg, very young man, born 1901, and created the first form of quantum mechanics in 1925 at the age of 24. And then, very shortly after Heisenberg had created that, Schrödinger, quite a lot older, in the winter of 25-26, created what's called wave mechanics. Now, here are the first equations I'm going to show you. This is the famous Schrödinger equation, and I'll tell you basically what this equation means if I can. And it's a thing about quantum mechanics that you may not have learned so much. Quantum mechanics is very remarkable. It gives probabilities for either measuring, in the simplest terms, measuring positions or measuring speeds or momenta. But what is really remarkable, it isn't for individual particles. It's in principle for complete configurations. So if you had 3 particles in this room, what this wave function, this psi, this magical thing down here. What that tells you, when you do just a little bit of calculation with it, it will tell you that if you had 3 particles in this room, it will give you probabilities for all, in principle, all possible triangles that they can form in all possible positions and all possible orientations. It's just unbelievable what quantum mechanics does. And all the really mysterious things come from this fact, that it gives probabilities for complete configurations. So you have a probability for this triangle to be in everywhere in this room, but also for the triangle to be much larger and different shapes and things like that. It's really extraordinary, and I can't do terribly much more than tell you that, otherwise I will not get to the end of my story. And the person who gave the interpretation of Schrödinger's wave function, which I've just more or less given you, was Max Born. So he was a very important figure in this story. And I'll just say I was the only one of the great figures of quantum mechanics that I have had a chance to talk to was Max Born. And I went to him, I had an introduction to see him in 1964. And I went to him saying that Einstein's idea about time was wrong. And he listened to me very patiently for a bit. And I was talking to him in German, but he was very fluent in English. And after about half an hour, he suddenly broke into English. "Young man, I have to tell you, you're going about this thing, physics, in quite the wrong way. I can assure you Einstein is right." Anyway, I was mad enough to continue in my madness. So now we go on, and now we're going to come to the sort of the crux of the mystery of time. Is about just a bit over 50 years ago, people started seriously trying to reconcile the basic facts of quantum mechanics with the basic facts of general relativity. Now, a key thing about that early discovery of quantum mechanics by Heisenberg and Schrödinger was essentially they created quantum mechanics in Newton's framework of absolute space and time. It's a rigid framework which they just took over pretty well uncritically, and they couldn't do any better because you have to go step by small step. That's what they did. But it's clear that can't be right if general relativity is also right, because according to general relativity, space is constantly changing all the time and generating time more or less along the lines that I described. So how do you reconcile that with quantum mechanics? How do you put the two together? And that is the great problem which has existed now for over 50 years. And we still haven't got the definite answer. There's lots of people, everybody's got their own ideas of the way forward. I've got my ideas, Lee down here's got his ideas, and the string theorists have got their ideas, and so on. And we're trying to do it. Now, one sort of picture has come out which has a certain sort of definiteness to it, and this came about because of the efforts of John Wheeler, the man who coined the term black hole, and he pushed someone called Bryce DeWitt to work on the problem of quantum gravity, the quantum theory of dynamical geometry. So there's John Wheeler, and here's Bryce DeWitt, who was a bit of a crusty old boy, but great to have discussions with. I was lucky enough to talk to him on a few occasions. And in 1967, he found an equation which is called the Wheeler-DeWitt equation. What's so enigmatic about it is it's an equation which purports to describe the quantum universe, and there is not a trace of time in it. It seems to describe a completely timeless universe. And that's what's called the problem of time. And it's been around a long time. And Bryce referred to it as, he used to call it, that damned equation, and I only found it to get John Wheeler off my back. I did once go and talk to a very eminent physicist about the Wheeler-DeWitt equation and why there are complex numbers in quantum mechanics. And he said he didn't know anything about quantum gravity, and I'd have to tell him. So I started telling him about the Wheeler-DeWitt equation. And when I got to the punchline that there was no time, this was the famous Sir Rudolph Piles, great physicist. He said, "So much the worse for the Wheeler-DeWitt equation, it's wrong." So this slide here just summarizes the problems in quantum gravity. So the original quantum mechanics was formulated in a background just like good old Newton had formulated. And Schrödinger had a wave function, that wave function which tells you the probabilities I was about, and I need to walk over here, you can barely read it. It depends upon positions in absolute space, and it depends upon Newton's absolute time. So that's there. And then it's governed by an equation where there's a t comes in it. There's the mysterious square root of -1 comes in it. This is the famous equation that Schrödinger discovered. So there's time in there, and then there's something called the Hamiltonian, which acts on the psi and governs how fast the probability, the wave function changes. So that's the standard picture in quantum mechanics. But when you go to quantum gravity, where this Newtonian background, this framework of absolute space and time has gone, you suddenly get something quite different. You get a wave function of the universe, and I'll say a little bit more about what it is, and it just doesn't have any time. The time is no longer in it. And it just depends upon the configuration. In my triangles, it would just depend upon which triangle you've got. It would give probabilities for each triangles. And so here it is, the wave function. This is the famous Wheeler-DeWitt equation in which time doesn't appear. So what does that mean? It's saying, in my toy model, it's saying that there's just a probability for this triangle, which doesn't change. It's given once and for all. And there's a probability for that triangle, and it doesn't change once and forever. And if we're only talking about a three-particle universe, there's all the possible triangles you could have, and you might as well put them all down in a heap and write the probabilities on them. One has a bigger probability than the other, and they don't change, and they're sitting there for all eternity as if they were in a morgue. That's the picture that emerges from the Wheeler-DeWitt equation. So no wonder people are a bit disconcerted by it. So is there any way we could actually recover a notion of time? So I'm just going to sketch. So up to now, there are certainly physicists, I dare say there's some in the audience, who would disagree with what I've said. But it's not all that controversial, what I've said. It's the Wheeler-DeWitt equation is hard to avoid. There's sort of architectonic structure in both quantum mechanics and in general relativity that when you put them together, it's going to lead to something like that. And you can, in simpler models, you can see it very directly. So we're talking about a relative configuration. If we had a universe with 100 particles in it, you'd have a probability for this, which was given for all eternity. And where is life? Where is time in that? But remember, out of 100 dots, a skilled cartoonist can make quite an interesting story if the dots are in the right position. So let me show you something else. This is a very famous photograph that same Ernst Mach took when he discovered shock waves. The sonic bang. Mach is the man after whom the Mach numbers are named. And this is a flash photograph taken in the 1880s of a bullet piercing a membrane at supersonic speed. And here are the shock waves going out from it. Now, give this photograph to a fluid dynamicist and tell him the density of the air through which that thing is going, and he can tell you the speed at which that bullet is traveling. Now that's a static image. It essentially has not changed since Mach got it about 130 years ago, and yet it actually contains information about motion. So something static can tell you about motion. And I call that a time capsule. And they're all over the place. So I define a time capsule as an unchanging structure that contains substructures that can be interpreted as mutually consistent records of a past that unfolded in accordance with definite laws from a special initial condition. And that's actually what happened with geology. Just think about, this is a man who created the first geological map and made very important discoveries in geology. 200 years ago, 220 years ago, most of humanity thought, or the Christian world at least, thought that the world had been created somewhat over 6,000 years ago. The geologists looked at rocks and fossils and found all sorts of fascinating correlations between them, very striking. And they asked themselves, this is a striking phenomenon, what can explain it? And they hit upon the idea of deep time, that the present state of the Earth must have arisen through a long process in time, governed by laws, that gave rise to what we have now, created these records. And this is a perfect example of a time capsule. Essentially, the evidence that led them to this great conclusion is still there, essentially unchanged. You can go out and look at the rocks that they studied, and they're still there unchanged. So that, I think, is very significant and shows that something is static, can at least contain strong evidence of time. So if you think about it, the whole universe, everything we know, is a colossal time capsule. And our belief that there was a past, even our own belief that we have a past and that I was once a boy, is actually all based on the evidence in the present. So the presently observed universe is just one huge time capsule. Everything tells one huge story about birth in the Big Bang. We get that from cosmology and astronomy. We have the geological record. We have the DNA in all living organisms. We have our own memories. And there's many, many more examples. And it's an unbelievably rich story. And I would say the most significant empirical fact about our existence, about the world, is that it is teeming with time capsules. And they're all mutually consistent, amazingly. Now, how can this have come to be in this timeless picture? Now, there's something which I think is very important. This is what I call Platonia. Now, let me just go back to my example of a triangle. Each point here in this picture here is a possible configuration of the universe. It would be a possible triangle in there. And there's only a limited number of triangles, so you can't have all of them. But what is very striking when you think about all possible configurations that you can have of a given system is that there's always one which is uniquely distinguished. And I call it point alpha. In the case of three particles, the equilateral, when they form an equilateral triangle, that is the most uniform state that the system can have. And it's what I call point alpha. And then from point alpha, you go out and you find ever more complicated, richly structured configurations. There is no point omega in this timeless realm of possible configurations of the universe. It goes from a boring beginning to an ever richer future. And I think there are two great asymmetries in existence. There's our own personal asymmetry between birth and death, and there's this colossal asymmetry in the Platonic realm of possible configurations. And somehow or other, I believe that it's the asymmetry of the configuration space with something like the Wheeler-DeWitt equation defined on it, which puts the probability, the most probable configurations on time capsules. And that might be the one now here, where we are now. And there are sort of strings of them which look like they're classical histories. They look like evolving universes where we are now here. And they're all sitting there of necessity. They are there by logical necessity. All the cartoons that have ever appeared in newspapers made out of 100 dots are sitting in their own Platonia of possible arrangements of 100 dots. Most of those arrangements are utterly dull, but there are very interesting ones among them. So that's my idea of perhaps how our sense of time kind of arisen. There is the question then, how on earth does it come about that you see my hand moving and I see it moving? Now, in philosophy, they make a distinction, and it was first clearly made by Galileo, between what are called primary and secondary qualities. Galileo said that there are things that I really think are out in the world. That's objects that have shapes and that they're moving and bumping into each other and doing things. So he comes up with this wonderful passage here. To excite in us tastes, odors, and sounds, I believe that nothing is required in external bodies except shapes, numbers, and slow or rapid motions. I think that if ears, tongues, and noses were removed, shapes and numbers and motions would remain, but not odors or tastes or sounds. The latter, I believe, are nothing more than names when separated from living beings. Such as tickling and titillation are nothing but names in the absence of such things as noses and armpits. I told you Galileo is a great writer. And the Wheeler-DeWitt equation suggests to me that Galileo's distinction is right, but we should move one thing that Galileo called a primary quality to a secondary one, and that is motion. We're all familiar with the fact that we see colors, or nearly all of us. I hope I'm not offending anybody who's a bit short of color vision. But all physicists say, no, this is just a wavelength. There aren't any colors out in the world out there, really. That's just something consciousness put into our brain. Now, what evidence do we have for the past? I would say it's our memories and the fact that you see my hand moving. And if I move it fast like that, you actually see the hand in all those positions at once, and you have that sense that it's moving. Now, is it inconceivable that nature somehow, through consciousness, is fooling us? That there isn't really any motion out there? There's only time capsules and this mysterious wave function of the universe that somehow or other through consciousness is telling us that we're seeing motion. I think it's a possibility. I believe that we need a deeper understanding of consciousness. Let me just mention that there was the famous Bishop Berkeley, who said that the external, he goes even further than I'm suggesting, a long way further. He's suggesting there's no external world at all. Now, believe me, I do believe you're there. And you're sitting on chairs. Now, Bishop Berkeley questioned that. He said there are just minds and God who puts these images and experiences into those minds. But they're also mutually consistent. It leads us to believe that there is a world out there. Now, that's a logical standpoint, and for a while I have to say I did take it very seriously, but then I have to say, why did God go to such immense trouble to make it really seem so definite that there is a world out there satisfying these wonderful laws that Einstein and Schrödinger and Heisenberg found? I think there's a problem one way or the other. So wonderful as Bishop Berkeley was as a writer. But let me say about this business about motion, we do know from neuroscience that the brain tells us many lies. It creates a narrative and shows us things which are not true because it thinks that's what we should see or experience. So maybe my idea that time is created by, but motion is created by consciousness is not so far off the mark. Let me come more or less to the end now. This is my favorite painting. It's by Turner. I love Turner. I mean, this is fantastic. 67 years old, and he claimed he had the sailor's time to the mast so that he should experience the full fury of the storm. But look at the picture that he produced, and that sense of motion, that whirling thing. So, you know, if Turner can do that with a picture, perhaps when I do that, nature is also creating the impression of motion when it isn't really there. I'd like to have that back. That's a much beloved sun hat which I bought in Argentina. So thank you very much indeed.
Support Ontario's public television. Donate at tvo.org.